Okay, this is your art master, Sir Bismarck. We are back again on our differentiation. Today we are going to take a look at our differentiation that deals with the first principle. Now, when we take a look at the first principle, it has a formula which says that dy over dx equal to the integral of f into bracket x equal to the limit of h approaches 0 into bracket f into bracket x plus h minus f of x all over h. Now, what does it mean? This is a function given to you. What it means is that wherever you see x in the function given to you, you substitute x plus h over there. After you are done with the substitution, then you minus the same function again from it, then all over h. Now, h approaches 0 means that during your final solution, wherever you see h in your solution, you substitute 0 into this, and then you find your differentiation over there. Now, let's see how the formula works. So, our dy over dx will be equal to the limit h approaches 0 into bracket 2 into bracket x plus h or exponent 3 plus 3, then minus the original function again, which is what, 2x cubed plus 3 into bracket all over h. Now, what do? We have to expand this bracket here. Now, this is exponent 3. So, for us to expand this, we must use the Pascal triangle to expand this bracket, which says that 1, 3, 3, 1. So, I'm going to use the Pascal triangle to expand this bracket. Then, I'll be heading to dy over dx equal to the limit of h approaches 0 into bracket 2. The first x will take the 1, which will be 2 into bracket x exponent 3 plus 3xh squared plus 3xh squared plus h cubed plus 3 minus 2x cubed plus 3 all over h. Now, after you are done with the expansion using this Pascal triangle, the next thing you are supposed to do is what? To expand this bracket over here. So, our dy over dx, the limit of h approaches 0 is going to be 2, or multiply that will give us 2x cubed plus 6x squared h plus another 6x squared plus 2h cubed, then plus 3 all over 2x cubed minus 3 all over h, bracket close. Now, from look at things, we can see that we have 2 exponent 3 here, another minus 2 exponent 3 there, which are like them, so these will cancel this. Then we have plus 3 another minus 3, so this will cancel that. Now, we are heading towards this over here, this and this and this. So our dy over dx equal to the limit of h approaches 0 into bracket 6x squared h plus 6x h squared plus 2h cubed all over h. Now, when you take a look at this, what we have here, we can see that h is very common over there. So we can factorize the h out. We'll be heading to dy over dx will be equal to the limit approaches 0. H is common, so h will come out into bracket 6x squared plus 6xh plus 2h squared all over h. Now what do I do? This h will take off this. Then our dy over dx will be equal to the limit of h approaching 0. That will be left with 6x squared plus 6xh plus 2h squared. Now, from the principle says that h approaches 0. That means from here, wherever you see h in this function, we substitute 0 over there. So all this will be 0. So therefore, our dy over dx will be equal to 6x squared. So this is our final solution from the first principle. Now let's get to example 2 and see how it is done. Tune into the next chapter for example 2. Thank you very much.